Welcome to this essential lecture on research methodology. Today, we are diving into the preparation of tables and figures. As a researcher, your data is your most valuable asset, but raw data alone is rarely enough to convince an audience. We will learn how to transform complex numbers into clear, compelling visual stories that instantly communicate your scientific discoveries. Let us get started. To begin, let us think about why we even need to visualize data. Imagine trying to understand a sports team's 10-year performance by reading a massive, unformatted text document filled with thousands of numbers. It would be incredibly frustrating, and you would likely miss the most important trends. This is exactly why we use tables and figures. They act as visual translators. They take a chaotic sea of raw data and turn it into a clear, digestible story that anyone can understand at a glance. In the real world, policymakers and scientists rely on these visual summaries to make rapid, evidence-based decisions. Now that we understand the importance of visuals, let us define the two main tools at our disposal. In academic research, a table is a structured arrangement organized into horizontal rows and vertical columns. It is designed to present exact numerical values and complex categorical information efficiently. A figure, on the other hand, encompasses any visual display that is not a table. This includes graphs, charts, diagrams, photographs, and maps. The primary goal of both tools is to enhance comprehension. Most importantly, properly prepared tables and figures must be self-explanatory. A reader should understand them completely without needing to read the surrounding text. Knowing what tables and figures are leads us to a crucial question. How do we design them well? While preparing them might seem like a purely artistic task, it is actually governed by a core quantitative principle introduced by pioneer Edward Tufte. This principle is known as the data-ink ratio. It mathematically evaluates the efficiency and clarity of a figure. The ultimate goal here is to maximize the proportion of ink, or digital pixels, that actually presents core data. At the same time, we must minimize the ink used for decorative, non-essential elements like heavy grid lines or three-dimensional effects. Let us look at the mathematical formulation of Tufte's principle. The formula is R equals D divided by T. Conceptually, this equation helps us systematically strip away clutter. The symbol R represents the data-ink ratio, which is a dimensionless number between 0 and 1. The numerator, D, represents the amount of ink used exclusively to display the actual data points, lines or bars that carry informational value. The denominator, T, represents the total amount of ink used to print the entire graphic, including axes, background colors, and borders. When the data ink D increases relative to the total ink T, the ratio approaches 1, meaning the figure is highly efficient. If total ink increases without adding data, the ratio drops. Before we move on, let us see this formula in action with a conceptual example. Suppose we have an initial figure with a certain amount of data ink and total ink. We calculate our initial ratio. Now, imagine a researcher decides to make the graph look fancy by adding unnecessary shadows and heavy background grids. What happens physically? The data ink remains exactly the same because no new information was added. However, the total ink used to print the graphic has now increased. Because the denominator is larger, the overall ratio drops. This lower ratio is a mathematical indicator that the figure has become cluttered and poorly designed. The physical meaning is clear. Extra ink without extra data hurts readability. Now that we understand how to evaluate visual efficiency, let us apply this to constructing a table. If you write out experimental results in a standard paragraph, it makes it incredibly hard for a reader to compare groups quickly. To solve this, we construct a formal academic table by defining its essential structural components. Instead of viewing a table as just a grid, we can think of it as a systematic assembly of specific, required parts. By breaking a table down into its fundamental building blocks, we ensure that the final presentation is both accessible and professionally formatted. This brings us to the conceptual equation for building a table. The formula states that C equals H sub T plus B sub H plus S plus B sub D plus F. Let us break down what each symbol means. C represents the complete academic table. H sub T is the title heading, providing a brief label at the top. B sub H represents the box head, which holds the column labels. S is the stub, the left-hand column listing your categories. B sub D represents the body data, which are the actual numerical values intersecting the rows and columns. Finally, F is the footnote at the bottom. If any of these variables are missing, the table is incomplete. Let us put this structural formula to work with a concrete example. A researcher has collected data on the average test scores of 3 different study groups. We are given that Group A scored 75 with a standard deviation of 5.2, Group B scored 82 with a standard deviation of 4.1, and Group C scored 89 with a standard deviation of 3.8. Our goal is to present this raw paragraph data in a formal academic table. We choose our structural equation because it guarantees no essential part of the table is forgotten. We will now build the table step by step. Now we will prove how this equation systematically generates a perfect table. In this first chunk of our derivation, we are setting up the framework. We start by defining the title heading, which gives the reader immediate context. Next, we establish the stub. This is our leftmost column, and here we list our independent categories, Group A, Group B, and Group C. Then we create the box head to label our columns, specifically mean score and standard deviation. The mathematical reasoning here is about creating a coordinate system. The stub provides the y-axis categories, and the box head provides the x-axis variables. This framework prepares us to insert the actual data. Continuing our derivation, we now fill in the framework to reach our final result. We insert the body data, placing the exact numerical values at the intersections of our stub rows and box head columns. Finally, we add the footnote at the bottom to clarify any abbreviations. By summing all these components, we have successfully derived the complete table. The intuition behind why this structured approach works is that it aligns with how the human eye scans information. Because we organized it this way, a reader can instantly scan down the mean score column and effortlessly see the progression from 75 to 89. The data is now accessible and professional. So, we have proven that structured tables work beautifully. This brings us to figures, like graphs and charts. Just as a messy paragraph hides data, a poorly designed visual can actually mislead the audience and obscure your findings. To fix this, we must systematically remove non-essential elements from our graphs. By identifying parts of the graph that do not represent actual data, we can subtract them. This process of subtracting decorative ink directly increases the clarity and professionalism of the figure, ensuring your actual research findings shine through. To achieve this clarity, we use the ink reduction equation. The formula is T new equals T old minus the sum of E sub B, E sub D, and E sub G. Conceptually, this is a subtraction problem where we remove waste. T new is the new total ink after optimization. T old is the original total ink of the cluttered figure. The variables inside the parentheses represent the waste. E sub B is the ink used for a dark background. E sub D is the ink for three-dimensional effects, and E sub G is the ink for heavy grid lines. When we decrease these waste variables, T new becomes smaller, which physically means the graph becomes cleaner and easier to read. Let us see how this subtraction works on a real problem. A student has created a bar chart to show the population growth of a city over 4 decades. However, the chart includes a dark gray background, three-dimensional shading on the bars, and heavy black grid lines every 10 units. The goal is to improve this figure so it is suitable for a formal research publication. We choose the ink reduction approach because it gives us a mathematical checklist of what to delete. By identifying the specific elements that carry no population data, we can clean up the chart without losing any actual information. Now we will prove how this subtraction transforms the graph. We start by identifying our non-data elements, the background, the 3D effects, and the grids. We mathematically subtract these from the original total ink. The reasoning here is simple. If an element does not represent a number, it must go. By doing this, we flatten the three-dimensional bars into simple two-dimensional rectangles and remove the dark background entirely. The intuition behind why this works goes back to our first formula. Because the actual data ink remains unchanged while the total ink decreases, the overall data ink ratio increases. This mathematical reduction translates visually to a stark, clear graph. Now that we have mathematically derived the optimized figure, let us look at the visual result. On the screen, you are seeing a side-by-side comparison of the exact same data. On the left is the original chart with a low data ink ratio. Notice how the dark background, the heavy grid lines, and the 3D effects distract your eyes. It feels heavy and cluttered. On the right is our optimized chart with a high data ink ratio. We have removed the background, flattened the bars, and erased the heavy grids. Notice how your eye is now drawn immediately to the heights of the bars, which represent the actual population data. This diagram perfectly illustrates that in data visualization, less is almost always more. To wrap up our lecture, let us review the most important ideas we have covered. First, remember that tables and figures are essential tools that bridge the gap between complex raw data and human understanding. Second, always adhere to strict structural rules, like our table construction equation, to ensure your visuals are completely self-explanatory. Finally, always strive to maximize your data ink ratio by systematically removing decorative clutter. You now have the mathematical and conceptual tools to make your research papers significantly more impactful. Great job working through these concepts today.